Hello. So today I'm going to do part 2 of eigenvalues and eigenvectors. Okay. So in particular, how to find the eigenvalues and eigenvectors of a given matrix A. And A has to be square. We're going to focus on 2 by 2, but these two steps work for a 3 by 3 matrix or a 7 by 7 matrix. Okay. First thing you do is you solve the determinant of the matrix A minus lambda I equals 0. That's a polynomial equation for lambda. The solutions of that polynomial equation are the eigenvalues, lambda 1, lambda 2, etc. And then step 2 is for each of those eigenvalues, lambda j, we're going to solve A minus lambda ji times Vj equals 0. We're going to solve that to find the eigenvector Vj corresponding to lambda j. Okay, so I have a few things I want to go through kind of quickly so this lecture doesn't take, an hour. All right. First thing is our defining equation for eigenvalues and eigenvectors. I talked about this previously. AV equals lambda V is the defining condition for an eigenvalue lambda eigenvector V. And one thing that's really important that I forgot to say yesterday is that V cannot be the zero vector. If you think about it, the zero vector works for any lambda, right? Because I get 0 on the left and 0 vector on the right, and they're equal. So you only get an eigenvector and the corresponding eigenvalue if you have a solution with a non-zero vector V. Okay. Then a few other things. I've been talking about all these I's. I is the identity matrix. I times a vector is the same vector. Here's an example. 1, 0, 0, 1 times 3, 5. If I do the matrix multiplication, I get 3, 5. So we have an eigenvector, a 2 by 2 identity, a 2 by 2 identity matrix, 1, 0, 0, 1. A 3 by 3 identity matrix with ones along the diagonals, etc. And often we just call it I, and you can tell from the context what size is. So IV equals V for a column vector V. We also have this determinant. What's the determinant? The determinant of a 2 by 2 matrix, A, B, C, D, is A times D minus B times C. Kind of think about going down this way and then down that way. A times D minus B times C. Okay, we might occasionally have to worry about 3 by 3 determinants, but not on your homework today. Okay, and then finally, going way back to a PDF that I posted for the class on February 26th, we talked there about a matrix equation. M is a matrix. MC equals D. For C and D vectors, and M a square matrix, MC equals D has a unique solution, C equals M inverse D, if the determinant of M is non-zero. On the other hand, if the determinant of M is 0, then MC equals D has either no solutions or infinitely many solutions. A little bit of theory there. Okay. But you remember it has the something about this too, that M inverse, the inverse matrix of M, exists exactly when the determinant of that matrix is non-zero. And we say that M is a non-singular matrix. Okay, well, that's a handful. Well, let's head right into it. Okay. So let's rewrite this equation here as a V equals lambda I V. We do that, so if I bring this over, I get a V minus lambda I V is the zero vector. And we know that it's a little bit like factoring an equation. We solve an equation, we like to have something equals 0. So here, this is the 0 vector. And not only that, but here's a matrix times a vector. This is now a matrix times a vector, where before it was a scalar. So now this is a matrix. It makes it nice. We can group these together and get A minus lambda I V. Oops, that was a vector V. Is 0. So this is like the M that we talked about here. This has a unique solution. MV equals 0 has a unique solution. V is M inverse 0 if M inverse exists, or if the determinant of M not equal to 0, right? So this matrix times a 0 vector is the 0 vector. So the only solution to this equation, or this equation equivalently, is V equals 0 if the determinant of A minus lambda I is non-zero. Okay. Let me just say this. Okay, I can conclude this. If the determinant of A minus lambda I is non-zero, in other words, the determinant of M is non-zero, the only solution to this equation, or that equation, is V equals 0. And V equals 0 isn't allowed to be an eigenvector. Okay? So we also get if the determinant of A minus lambda I equals 0, then lambda is an eigenvector. Okay? Strictly, you might remember what I said before. This equation here either has no solutions or infinitely many solutions for V if the determinant of this M is 0. Well, we know it has one solution. It has V equals 0. So no solutions is ruled out. It must have infinitely many solutions. So that's why we can conclude this. But that's already what I did on step 1. So now I can get rid of all of this, right? That's why step 1 works, okay?